Good morning class and welcome to another lecture in sustainable energy technology. In the previous class, we started our discussion on electrical energy storage systems and we looked at traditional capacitors. We saw that the traditional energy storage, traditional capacitor based energy storage has ability to store only a little amount of energy, about half a joule, based on the capacitance and the voltage values that can be sustained across the charged plates. Remember, the energy E was equals to half CV square, where C was the capacitance in farad and V is the voltage across the plates. Okay. So today we will discuss two advanced types of capacitors which have significantly larger values of the capacitance C, so that larger amounts of energy can be stored. The first type is called electrolytic capacitors. So here the anode, that is the positively charged plate, is made of a metal like aluminium, tantalum, or niobium that forms an insulating oxide layer over the anode surface through the anodization process. So these are specific types of metals that are being used as the anode material, that when it is being charged by positive charges and passes through what is called the anodization process, it produces a small insulating oxide layer on the top of the surface. Okay, so like aluminium oxide, tantalum oxide, niobium oxide, etc. Okay. This oxide layer functions as a dielectric material. So the actual dielectric material which is preventing the transfer of charges from the anode to the cathode is nothing other than the oxide of the anode metal itself that has grown on the surface of the anode. Okay. The rough and thin oxide layer increases the A by D ratio of the dielectric. Further, the relative dielectric constant of aluminium, tantalum, niobium oxides are very high. So, let's look at the structure of what I am talking about. You have, let's make it a bit more professional. So, here we have the anode material. This is the positively charged anode, and you have the positive charges along the surface of the anode. This anode metal is made of aluminium, tantalum or niobium metal, and during the anodization process, when the anode is getting positively charged, a very thin oxide layer, so this thickness is significantly magnified. Okay, this may be a few less than 1 millimeter, maybe a few tenths of a millimeter thick oxide layer that is being formed, and this is the thin rough oxide layer on anode surface. Okay. So, because the presence of the oxide layer makes the surface quite rough of this anode, the relative contact area of the dielectric with the metal surface increases. Why? Because if it was a straight line, the total length will be just the straight line L. But here we have a rough surface. So, the effective length of the effective contact length is increasing significantly, and the effective contact surface of this rough surface with the dielectric oxide increases significantly. So, roughness increases contact area A. Very thin oxide layer, so D is very small. Okay. So, this is only the D, the thickness D, the layer thickness D. Okay. And furthermore, the dielectric constant of these materials are quite large. So, E, the value of epsilon is of the order of 10 for alumina, of the order of 26 for tantalum oxide, and of the order of 42 for niobium oxide. Okay, niobium is Nb. Okay. So, remember, your capacitance is given by epsilon naught, which is the permittivity of vacuum, which is constant, into the dielectric constant epsilon into A by D. So, in these examples, we are seeing that the epsilon is larger, the dielectric constant, and this A by D ratio is also very large because the roughness is increasing the contact area A, and the thickness D has also decreased significantly. Okay. Now, the question then is, where is the rest of the system? where is the anode and the and what is there in the gap between the anode and the cathode. Okay. So first, let us draw the anode. The negative charge, the cathode section. So the cathode is a traditional cathode. So we will just draw it. As before. Okay. So we have the negative charges here. Now, in between the anode and cathode, what we have instead of a dielectric material is an electrolyte. Okay, so what you have is some sort of a this is a electrolyte. Okay, this is your cathode, this is your anode. Because the electrolyte is here, this electrolyte is actually a carrier of ions. So, because of the presence of these negative charges can actually be transported through the electrolyte, getting attracted to the positive charges here in the form of negative ions, and these negative ions can migrate here. So these are the negative ions that has migrated through the electrolyte to the surface of the oxidation layer, which is acting as the dielectric. So these negative charges are creating negative charges in the electrolyte, and the presence of the positive charge here causes the electrolyte to get the negative charges of the electrolyte to get attracted and collect on the opposite side of the metal oxide layer. Okay. So what this means is go to the next page. The rest of the gap between cathode and anode is filled with an electrolytic substance that can transport the negative charge of the cathode plate to the dielectric oxide surface. The electrolyte effectively extends the cathode to the surface of the metal oxide, dielectric layer. Understood? The electrolyte may be a liquid or a gel or a conducting solid that can form polymer bonds with the rough oxide layer so that there is complete contact. Okay. So the basic idea here is this electrolyte can be a liquid or a gel, that is an aqueous kind of a system or a gel type of a system, or it can be a solid which can form polymer bonds with this oxide layer so that you get good contact between the dielectric and this electrolyte material. If it's a liquid or a gel, then good contact is given because it can form, the liquid or a gel can contact with a rough surface also. Okay. In solid, the problem is the solid surface and the dielectric can have gaps. Okay. So that will reduce the contact area and that will impact the capacitance ability. Okay. So then if you are going for a solid electrolyte, it should be first be conducting and it can form polymeric bonds between the oxide and the solid electrolyte so that you get good contact. Okay. Now, one disadvantage of so this is called our electrolytic capacitor because the main gap area is made up of electrolyte instead of a dielectric medium. Okay, so that's why we call this electrolytic capacitors. Now, one issue with this kind of a system is that the anode and cathode are distinct. The anode and the cathode cannot be reversed, right? So anode is basically a specific aluminium, niobium or tantalum metal on which you have the oxide layer, nothing like that in the cathode. The dielectric is in contact with the cathode plate directly, while anode plate there is the dielectric oxide layer. Okay. And hence the charges of the two plates cannot be reversed. So, these capacitors require DC voltage. Okay. So you need a small transformer to convert the usual AC current into a DC current and a DC voltage so that the polarity of the anode and the cathode is not reversed. Okay. So in a typical capacitor, you have two metal plates, the dielectric, and the two plates are completely symmetric. So it can work with a AC current directly because nothing changes if the polarity is reversed during the cycles of an AC current. Okay. These types of capacitors have a unique anode and a unique cathode. So the polarities of the two metal systems cannot be reversed. So that means that these capacitors require a DC voltage system. So specific energy density of electrolytic capacitors is of the order of 0.03 watt hour per kg. So it's still small. Okay. However, their specific power is large, of the order of 1000 to 10,000 watt per kg. Okay. They can withstand fast charge discharge cycles in a few second cycle time, and have very high cycle life of the order of 10 to the power 6 cycles or more. They also have high round trip efficiency. Of the order of 0.95. So let us understand all of these ideas together. So specific energy density of an electrolytic capacitor is still small, about 0.03 watt hour per kg. So despite the increase in capacitance, it doesn't increase the energy density significantly, and we will see why in a little bit. But still, it is better than a traditional capacitor, and you have specific energy densities of around 0.03 watt hour per kg. So small amounts of energy can be stored. However, the capacitor, these types of capacitors can store charge and discharge that energy at very fast rates. So the rate of absorption and the rate of transmission of electrical energy is very fast. So the specific power, that is the rate at which it is transmitting this energy back to the system which needs it, is quite large. It's around 1000 to 10,000 watts per kg. So if you need small amounts of energy but high at high powers, then this kind of capacitor is very good. Okay. They can also withstand very fast charge discharge cycles of the order of a few second cycle times and have very high cycle life. So more than a million cycles, and still their life will not be spent. So quick charging, discharging requiring high power but modest amounts of energy. That is where these types of electrolytic capacitors are very good. They also have high round trip efficiency of around 0.95. So 95% of the energy stored in these capacitors can be recovered. So they are ideal when high electrical power is needed over very short times. Okay. Example, startup of heavy electrical machinery. Example, compressors and pumps. So this is a very specific application of these types of electrolytic capacitors. When you are starting up a heavy machinery, the initial startup requires a lot of energy, okay, for a very short period of time to start the motor for rotating. And this type of systems, the electrolytic capacitors, can give you that initial high power required to jump start the machine. Okay. But it can also be used in other places like very quick energy voltage or power fluctuations in a renewable energy grid. This electrolytic capacitors can transmit small amounts of power to do that. Okay. Can also be added to renewable energy grid systems for power quality management and deal with sudden spikes in demand / supply. Okay. So these two are applications of these kinds of systems. All right. So this is the electrolytic capacitor. In the next class, we will discuss the last type of capacitor which has been developed only in the last 10-20 years, which is the super capacitors or ultra capacitors, that is finding a lot of applications in the today's world. Okay. So thank you for listening, and we will see you in the next class. Thank you.